Good morning, all of you. My screen is visible. Hello.
Yes, sir.
Okay. See, today we'll see the IGBT, power IGBT, that is insulated gate bipolar transistor. So the name itself, it is a bipolar. So the device is a bipolar device. It is obtained from combination of the BJT and MOSFET. So we discussed the previous class BJT and MOSFET. I mentioned individually the comparison between BJT and MOSFET also. And some cases BJT is better and some cases MOSFET is better. So, and there is a disadvantages also there in the individual case because conduction losses are less in case of BJT and conduction losses are more in case of BJT and switching losses are more in case of BJT and then switching losses are less in MOSFET like that. So they have their own advantages and disadvantages. That's why what we will do is we make use of advantage of BJT and MOSFET and we'll bring you a new device that is a IGBT. So low on-state classes, but driving requirement of BJT is complicated, and MOSFET is a high on-state class, but driving requirement is simple, and only voltage is applied between gate and source. So once the voltage is reaches threshold voltage, then the device will be turned on, and if we remove that voltage, gate and source, then we can turn off the MOSFET. So that is the case of MOSFET. In the MOSFET, collector and emitter. So now what we have to do is collector and emitter circuit of BJT are combined to form as a new device. So here the two things, one is a input side and output side. As per our explanation of previous BJT and MOSFET, once the device is conducting, there is a loss in a MOSFET. That's why what we will do is we'll make it as a MOSFET in the input side and BJT is in the output side. So if you arrange such that, then we can get it as a new device is a IGBT. So what we will get, we will take only the advantage of BJT and MOSFET to get as a IGBTs. So now we'll see the combination of BJT and MOSFET in this diagram. If you notice that, you can see there is a MOSFET, that is a gate drain source, and BJT base collector emitter. So you club these two devices, then there is a gate, then collector, emitter. Some books they represented drain and source also. It's not a matter. You can see that it is nothing but a collector and emitter. In general word, we can consider as a gate, collector, and emitter. So now, okay, how it is forming, we can see here. There is a MOSFET and then BJT this side. Then we can get it gate, collector, and emitter. Same the device symbol also. You can see this. It is a combination. You can see the gate is input side and then collector and emitter. So once the device is on, then as usual the switch will be closed. Now you can see the another equivalent circuit. This diagram will represent. Can remember what is this? It is similar to that of a two transistor model of SCR. So like this, there is a combination of these two to increase the current capability and all. You can use this way. And this is a like a two transistor model. And then it is connected to the MOSFET. And finally, we will get all the three terminal. One is a gate, then collector, then emitter. So this is the symbol of a IGBT. Now you can see this three terminal. As I said, there is a gate, collector, and emitter. Current flows from collector to emitter. When it will be collector to emitter? So if you apply voltage between gate and emitter, so that means IGBT will turn on. If you apply voltage between gate and cathode, gate and collector, then automatically you can see here where we have to gate and emitter. So these two terminal, if we connect the voltage, then automatically device is going to be turn on. So when gate emitter voltage is removed, that means the gate voltage is removed, automatically the device is going to be turn off. On-state collector to emitter drop is very small, like a BJT. So on-state, this is the problem in case of MOSFET. You can see that once the device is on, that means on-state collector to emitter drop is very small in case of BJT. That's why we used BJT in the load side. But whereas if we keep that MOSFET in the load side, the device is on, you will get it as a lot of drop. So that is one thing. And whereas here input characteristics we can consider as a MOSFET related, and then output side we can consider as a BJT. So then we can say that voltage controlled bipolar device. So we are able to control the device in a voltage control manner. But individually there is a BJT is a current control, and then MOSFET is a voltage control. Because we consider this input side is a MOSFET, then the device is a voltage control bipolar device. So now scaling up the blocking voltage capability. So we are increasing the blocking voltage capability of the device. Now the objectives are to overcome the problem faced by the BJT and MOSFET, and then it act as a we can see that voltage control device. So whereas in case of previous MOSFET and BJT separately, so there is a MOSFET is voltage control device, BJT is a current control device. But now it will act as a voltage control device, and then it will be as a switch. Then it is a high efficiency and fast switching. So fast switching in the sense we can see that our application of the MOSFET, there is a high switching frequency we are using. So the reason is turn on and turn off times are very small, therefore we can operate this into high switching frequencies. Now this is the internal structure of a IGBT. You can see that as usual there is n minus layer will be there, drift region, that is common for all the power devices, and then P plus, N plus, and P and N plus, like this PN notation. So there is in turn I shown you the two transistor analogy as a thyristor model also. That construction part will be come into this picture. So now we can see this structure of IGBT. It is a like a MOSFET structure only. The layers, you can see that n minus 1 channel IGBT, the layers are P plus n minus and P. So same P plus n minus and P and n plus. So this is in turn is nothing but a thyristor fashion. And now to make P channel, this is a n channel IGBT. Suppose you want to make it as a P channel IGBT, then what we can do, like MOSFET time I told, no, if you change that doping levels, the layers, automatically we can able to reverse that, either it is a P channel or a N channel. Now what will happen, we can start with here is a N plus, then there is a P plus, then P minus, then N, then P plus, like this. It is going to be changed. If it is a, you want to make it as a N channel replaced by P channel, that this will be changing the doping type. And now the here IGBT case, P plus substrate is called as a injected layer. So this will be injecting layer, so electrons into the N minus layer, that is a drift region. So called N minus 1 layer is a drift region, so that is common. Thickness of the n minus 1 layer is depends upon the blocking capability. So that we noticed from the power diode onwards. So based on the thickness of the n-1 layer, the blocking capability, that is voltage blocking capability of the device will differ. And now P layer is called as, this layer is the body of the IGBT. Now the operation, you can see that this is the construction, or whatever layers we made in the construction, that will be in terms of the device. We can see that there is a structure of this T1 and T2 is similar to that of two transistor model. One base of the transistor 2 is connected to collector of the transistor 1, and base of the transistor 1 is connected to the collector of the transistor 2. So like that we arranged this side. And now there is a internal MOSFET, and as well as the transistor is formed to get it as IGBT. Now there is a T1 and T2. This structure is nothing but a SCR structure. Up to this model is like a SCR model. Now here gate serves as a triggering of the SCR T1, that is a transistor 1, because once if you give the gate signal here, then MOSFET will trigger. Then once MOSFET is trigger, what will happen? This is connected to the base of the transistor 1. Now there is a signal is passed through base to T1. So then what will happen? T1 will be turned on. So if the T1 is turned on, when it will be turned on? Once if you trigger the MOSFET. So when the MOSFET will trigger, when the gate source voltage beyond the threshold voltage. If you make it as this voltage is beyond the threshold voltage, that is a VGST, then automatically this device will trigger. Once if this is on, that is connected to the base of a transistor 1. Then once the T1 is starts conducting, then the T1 is conducting, then what will happen? This will be on. If this is on, this current is nothing but a base of a transistor 2. Then automatically transistor 2 also is going to be turned on. If transistor 2 is on, then that is connected to the base of a transistor 1. So then there is a regenerative loop is going to be created, and large number of carriers are injected into n- drift region. So there is a n- region is told, no, this large number of carriers are injected into the n-1 drift, n- drift region. This reduces the on-state loss of IGBT, whereas in case of MOSFET case, the n-drift region is not, carriers are not much, so that's why there is on-state losses are more. But now because of this process, we are injecting the more and more carriers onto the layer. So then automatically what will happen? We can see that drop is going to be reduces. When the gate is removed, then what will happen? The induced channel will be vanished, and then MOSFET will be turned off. So this is common logic. Whenever if you remove the gate signal, earlier we are passing as a gate voltage, then it will be trigger. Now once if you remove this, then automatically MOSFET will be turned off. Once the MOSFET is turned off, then in turn what will happen? T1 also will be turned off, and also T2 also will be turned off. So because of this MOSFET only T1 is on, because T1 is on, then the T2 will be on, there is a regenerative loop will be created. But once if this is off, then automatically T1 will be off, and then T2 will be off. If R1 is very small, T2 will never turn on, because we will see that the body resistance, that is also some of the protection we need to make it. Now MOSFET on state classes are high, hence the resistance of drift region remains the same. So because of that resistance remains same, the MOSFET on state classes are high. But whereas in this case, IGBT case, we are injecting the more charge particles onto the drift region, then the resistance will be, drop will be minimized. So that's what IGBT resistance of the drift region reduces, and when the gate is drive is applied, then what will happen? When the resistance is reduced, automatically P plus layer injecting the region. So that means resistance reduces because of the P plus injecting region. On state losses of IGBT is a very small when compared to the MOSFET. There is a two ways or a classification. You can say that IGBT. One is a non-punch through IGBT. Another one is a punch through IGBT. In the structure, if you see, one of the layer is missing now. Earlier structure and this structure, if you notice, non-punch through are also called as a symmetrical IGBT. The IGBT without N plus buffer layer is called, here there is a one more layer will be there, that is N plus buffer layer. If that is not present, then I can say that we call it as a non-punch through or a symmetrical IGBT. So the IGBT have symmetrical voltage blocking capabilities. So if the N plus buffer layer is absent, then this IGBT is having as a blocking capabilities are same under forward condition as well as the reverse breakdown voltages. These two equal forward and reverse breakdown voltages are same if the N plus layer is absent, and these are used for the rectifier type of the applications. So normally in case of rectifiers and all, we use as a thyristors, but if it is a low rating, then you can use it as a IGBT as well. But while you are using it is a non-punch through IGBTs we are using. Another one is a punch through IGBTs. This is also another name for this is asymmetrical. Asymmetrical means here N plus buffer layer will be present and voltage is forward as well as the reverse case voltages are different. N plus buffer layer is called as a punch through. Reverse breakdown voltage is less than the forward breakdown voltage. So reverse breakdown voltage and then forward breakdown voltages are different. Faster turn off times, hence they used for the inverters and choppers. So normally when the switching operations is major role in the case of a power electronic controllers. So why? Because any control you can take it, whether it is an inverter or in the case of a choppers or any for that matter maybe cycloconverter or rectifier, all the controllers operation is based on the switching operation. Whether you want to operate the device in the modes, two modes only, on mode and off mode. Once if you are turn on the device some duration, then you must be turn off. Whether you can apply natural commutation or a forced commutation, but our intention is to turn off the device after some duration. Again, you have to turn on the device. This is only the process throughout power semiconductor device used in a power electronic controllers. That is the reason the switching action, and also you can see turn on times and turn off times and on and off times are less, then the device cost also is going to be high. That is the because we need that type of devices to faster switching action. If you operate the device the faster rate, you can able to get the better improvement of the waveform also. That we will notice in the case of inverter and all. Inverter output we call it as a DC to AC. No, the AC will not be get pure AC in normal inverters, but we make use of the some commutating technique or some control techniques, that is a PWM technique. In turn there is a different types of techniques. So using the techniques we can able to turn on the device. So while you are turn on the device, we make sure that the waveform will get the pure sinusoidal in nature fashion, and also harmonics will be reduced. So that is the normal process actually, the control strategies. That's the reason we can see that faster turn off times preferably will use inverters and choppers. And the latch up in IGBT. So there is a small concept is there. Latch up means that remains in the on condition even if the gate is removed. So this phenomena normally we notice it in the case of SCR, because in the SCR case Once the SCR is turned on, device will not be turned off until unless current passes through the device below the holding current. But here there is a IGBT remains on condition even if you remove the gate pulse. But the SCR also, if you remove the gate pulse, the device will be remains in the on state. That is only our process in the case of SCR. But here there is some problem, because of that it will be happen cause of flash up. That is the current in p-type body region flows vertically as well as tangentially, so that we show no MOSFET as well as the structure of transistors, two transistors connected in that figure. In the body region resistance we used as a R something resistor we used sufficient to turn on NPN transistors, so T2. If that resistance across that body resistance we made R no there, so that value if it is sufficient to turn on the device T2, then eventually T1 will fire and then regenerative happen will takes place and device will continue to on. That's what I mentioned here. So once the T2 is on, then automatically T1 will be turn on. So regenerative takes place. Under this situation, gate has no control over the current flow. So that's the reason IGBT remains in the on condition. So this is the problem of that resistance. So that's why make sure that resistance value will be within the condition that drop is more than the specified of required of the transistor is turned on, automatically device will continue to conduct. Then how will you avoid that? So then we can reduce the body resistance. So this can achieve by using the special geometrical structure of a IGBT. So that body resistance is not, we are intentionally adding that, because we use this material, that resistance will be placed there, that will happen that resistance value. If that value is more than the required current across that base signal, and then T2 will be turned on, and if T2 is on, then automatically the device is going to be turn on continuously. So that is the problem. That's why to overcome that one, resistance value we can reduce. So this circuit should be designed in such a way that maximum specified current should not be exceeded. So that is what I mentioned there. The base current, specified current, if it is exceeded, then automatically transistor 2 will be turn on. So latch up can be avoided by increasing the turn off time and then controlling current gain of a T1. So then preferably we'll use as a only the resistance of that R1 will be reduced. So now the characteristics is more or less similar to that of MOSFET only. You can see that that's why I used as a two diagrams. Both is, this is one is a MOSFET and this is a IGBT, and as triggering process, no, like once if we give the gate and source voltage, if it is greater than threshold voltage, automatically MOSFET will trigger. Similar question in case of IGBT also, we are passing the gate voltage across gate and emitter, then the up to the threshold voltage, beyond threshold only it will be on, below that it will be remains in the zero, collector current will be remains zero. After that this current will be gradually rises. So that's the reason I mentioned two diagrams. In exam one is sufficient because it is a IGBT case. You just make use of any one of the diagram. Because of the both is same in phenomena, I used as two diagrams. It is not a matter. You can use any of diagram like MOSFET case. So all these things will be the same. It is a cutoff region or a ohmic region. Any these two regions only it is going to be operate. One collector to emitter voltage increases by fixing the gate source voltage, and the particular instant the current will be gradually changes. So this is the characteristics of an IGBT. Now whatever I explained there, I mentioned here the theory part. So current flows drain to source means here collector to emitter controlled by the gate signal. Then the source terminal is in the common because input and output of IGBT. And these characteristics we can see in our lab also. We have MOSFET, IGBT, BJT characteristics. Maybe in the next week you can able to do this experiment physically in our lab. There is experimental setup is there, and by changing that voltage, and when the device is going to be trigger, what is the threshold voltage. Once the device is conducting, what will happen the current. So all these things we can notice in our lab, because all the experiment you need to do in the lab purpose. So the current is non-linear when the drain current is low, and this is approaching to the threshold voltage, and this threshold voltage value 2 to 3 volts. And now there is a switching characteristics. So this is again same process, switching characteristics means on and off. The before turn off, turn on, device is in the off state. So once the device is in the off state, we need to turn on the device. How the device is going to be turned on? By applying as a voltage, gate and emitter voltage. If you apply, then gradually device is going to be turned on. And once the device is on, we'll see this here. What is our intention? We are this is the initial small voltage, and later on if you want to turn on the device, so what we want? We want to increase the gate and emitter voltage. Once if this voltage is increases gradually, once this point reached, what is this point? VGET means gate emitter threshold voltage, or you can say that IGBT threshold voltage. Once if that is reached, automatically device is going to start conducting. So up to that, what will happen? Collector to emitter voltage is same as the rated voltage. The reason is before turn on, device is in the off state, and this side I will show you. See, this is in the off state. So off state means what is the voltage? Same as the applied voltage, no, in the collector to emitter side. So that's the voltage will be remains in the same. And what about the current? Only small leakage current will be present. Now there is a voltage is gradually increases, then this is going to be dropped down gradually, and current is going to be increases. Once this current is increases to the rated, then automatically what will happen? Device is completely turn on, and it has to be dropped down this voltage to the very low voltage, only leakage, or you can say that drop across the device. So this process we can see that turn on process, that means delay time as well as the rise time. So now we can see that from rated to 90 percentage of the collector to emitter voltage, that is a delay time. And same fashion you can see that this leakage current from 0 or very less value to up to 10 percentage of its final value, that we call it as a delay time. And rise time is anyone you can explain this way also. Voltage changes from 90 percentages to 10 percentage of its final value. Which voltage? Collector to emitter voltage. The instant or between 90 percentage to, just a minute. Now we can see here there is a current changes from this point, that is a 10 percentage to 90 percentage of its final value, or else voltage drop from 90 percentage to 10 percentage of its final value. So this way we can able to define that delay time and then rise time. This is also called as a turn on time. And another one, once the device is on, then what will happen? You can notice here, once device is completely on, this will be remains in the same, current will carry that, and voltage whatever drop will be there, that voltage will be remains in the 0. So in that case we can see that this turn off time, so that is over, the turn on is over. Now we make use of a turn off the device. How the device is going to be turn off? The whatever charge particles are there inside the layers, it has to be removed. For that there is a fall time, delay time here for the turn off process, and then fault time here is a two fault times. One is a initial fault time, another one is a final fault time. So based on this value of intervals, we can simply define that what is the initial fault time and then final fault time, and finally sum of these three. So delay time as well as the fault time, that is initial fault time and then final fault time, we can able to get it as a total turn off time. So this way we can get that process. That's also I mentioned here in the theory part also. Turn on time, usually delay time and then rise time. And delay time is defined as the time which collector current rises from leakage current to 10%. You can see that this is a collector current, rises from leakage current or very small current because it is under forward bias condition, and from that to 10% of its final value. That is one thing. And also you can notice that voltage, that collector emitter voltage falls from rated to the 90% of its final value. So that we call it as a delay time. Another one is a rise time. You can see that time in which collector current rises from 10% to rated current or nearly 90%, or finally it is reaches to as a rated current. And the voltage you can see fall down 90% to 10% of its final value. So that we call it as a rise time. So some of these two we call it as a turn on time. And then fall time, turn off time, you can see that it is a three. One is you can say that delay time and initial fall time and then final fall time. So in that again same based on this interval. So delay time is nothing but a rated current to 90% of its final value and the voltage being raised. So from this what will happen? It is from the lower or drop voltage, from that the voltage is gradually rising. And then initial fall time is the time during which collector current falls from 90% to 20% of its final value. And you can see that collector current, there is IC current 90% to 20% of its final value. I call it as a initial fault time. And collector to emitter voltage also you can see that now it is going to be rise from 10% onwards. Why it is going to be rise? That the device is going to be turn off. Once the device is completely off, it has to be final voltage will get it. Then final fault time is during which the collector current falls from 20% to 10%. So that voltage will be rises to the final voltage. So this process we call it as a dynamic characteristics, on process as well as the off process. Another one, safe operating area of IGBT. So there is a maximum ID, because some of the parameters we need to consider and to find the safe operating region, like MOSFET in the yesterday's class we noticed. And similar fashion here what we consider that is a maximum drain current, or you can say in this case IGBT case collector current we call it as. Then permissible internal junction temperature, this also we have to consider, and the forward blocking voltage and reverse blocking voltage, maximum power dissipation and maximum gate voltage. So these are the safe operating regions we need to consider by considering these parameters. So in that some of the values are mentioned here. So maximum collector current or a permissible collector current of the IGBT is mentioned 200 amperes to 400 amperes. Then gate to emitter voltage, so that is a maximum gate voltage that will determine the breakdown of a SiO2, because in the gate terminal directly the metal is not contact with the body, in between SiO2 layer will be present. And collector to emitter maximum voltage is determined by the breakdown voltage of a transistor 2. Similarly, IGBT has 1700 volts blocking capability, and then maximum junction temperature is about 150 degrees centigrade. And we will see that forward region case and as well as the reverse breakdown case of safe operating regions. This we can see the diagram. In forward bias condition, maximum power dissipation is also limited by the maximum junction temperature. And AB, this you can see that region AB, this portion is represent the maximum limits of a drain current. It should not be beyond this, and that will be always less than the 100 volts. That is the case of voltage. At voltage is less than 100 volts and will represent this is the case of a drain current, and VDS is greater than 100, then the ID reduces the boundary. So then we can see that this region will be reduces because we applied the more voltage on that. And boundary CD, you can represent this one, represent the maximum voltage capability of a IGBT. So because in the x-axis is represented as a voltage, so this point is a maximum capability of the voltage of the IGBT. When IGBT operate as a switch, now it is going to be open and close operation, and driven by pulse signal. To turn on, we need to give as a pulse signal, and boundary of the safe operating area can be extended. So why? Because of this time durations, again the boundaries is going to be little bit extended, because once the device is turned on only few microseconds of time, then what will happen? Then the device will be absorbed very small amount of energy, and then junction temperature will be low and boundary of the region will increase. Suppose if you are operating only 10 power minus 4 microsecond, this is the boundary. Then if you further increases, this will give as a boundary. Like that, because of very small duration, the temperature rise can be minimum. So that's what same this diagram, and represented for the reverse bias condition and forward bias condition, the boundaries is going to be changed based on your operating time durations. So now we will see some of the advantages of IGBT. So there is a voltage control device, hence device circuit is very simple, and good power handling capabilities, and low forward conduction voltage drop of 2 to 3 volts, which is higher than of BJT but lower than of MOSFET of a similar rating, and positive temperature coefficient. Because of this temperature coefficient, the device is easy to operate in parallel. And then high speed switching capability, and the low gate current is sufficient to turn on the device. Relative simple voltage control gate drive when compared to that of the BJT and all. No commutation circuit is required because of voltage applied up to threshold voltage, it will be turn on, and if it will be open, the device will be turn off. So means voltage is removed. So that is the reason we can say that commutation circuits are not required when compared to the SCR. And gate have full control over the operation. So here only gate will control whether it is to turn on and turn off. And disadvantages are a static charge problem, like MOSFET also we required some across the gate and source, there is a capacitance is required that will be charged. Once it is charged to the threshold, it will be turn on. So that is the problem here also, because we are connecting that into the input side only. Costlier than the BJT and MOSFET. Obviously, it is a additional or hybrid device, the cost will be little bit more. So applications of this will be used AC motor drives. AC motor drive in the application is nothing but inverter operation, because inverter output is a AC. So inverter output is AC means then only we can use as a AC drive application. But DC drive means what? DC output we required. So in this case, whenever we are operating as high frequency operations, we can use as an inverter. So that is a AC drive application. As well as the DC side, there is a DC chopper applications also you can use it. All the DC relevant we will preferably use as a IGBT sender, because the control commutation circuit is not there. So that is the major advantage of this device. For higher rating applications or high rating application, commutation circuit is required, means it is a complicated, very high current is passing through that. Forced commutation to turn off the device, make use of this forced commutation circuit is very complicated. That's why in this case, inverter and chopper, normally forced commutation is required. But whereas if you use as a IGBT and all, the commutation circuit is simple. So that is the reason we'll use it. So UPS system and harmonic compensation. This is what compensation also is going to take place, and that type of fax controllers and all we can use as a IGBT. Now we'll see the different comparisons of MOSFET. So MOSFET and IGBT case, there is a voltage control device. So MOSFET is a voltage control device as well as IGBT also. The terminals are gate, drain, source, and whereas IGBT terminals are gate, collector and emitter. Input impedance is very high, and the input impedance also both because both is MOSFET in input side, and positive temperature coefficient, both cases are same, and on state voltage drop is large. So this is the problem we are going to overcome in case of IGBT, because in the MOSFET case there is on state drop will be large, but in this side output side we are using as a MOSFET, BJT. That's why IGBT has a very low on state voltage drop. Switching speed is superior to that of IGBT, and switching speed is inferior to that of MOSFET. At high ambient temperature, maximum current rating is reduced, and this will be ambient temperature IGBT is well suited, and current sharing between parallel connected MOSFET is poor compared to the IGBT. So that case it is a better. And now we'll see last topic of this unit, gate drive circuit for MOSFET and IGBT, because here both are in the same phenomena, same drive circuit, we can use it for MOSFET as well as the IGBT. So MOSFET is a voltage control device, consequently gate currents are not dependent on the drain current. So only here to drive, or you can say that to turn on, we required as a driver circuits. And then we can see that gate power required to maintain the MOSFET in the on condition is negligible. So only very small voltage, up to threshold voltage, we need to apply to trigger that. Gate protection of IGBT is functionally like a MOSFET. These drive circuits will be discussed on the applications of IGBT. Now we'll see the one by one. I will show some of the driver circuit of MOSFETs. You can observe that gate current required to maintain MOSFET and steady on condition is 0. Now there is a one small gate current representation here. What will happen? Gate circuit energy is used only to turn on and turn off the MOSFET. So here IG, so this is the current. IG plus is for the turn on process and IG minus is the turn off process. Under steady state condition it is not required, simply the current is not required once the device is on. And now during turn on, IG plus is applied to the turn on of the MOSFET. So this is the spike or pulse current. In turn, there is we are applying voltage that will leads to the current pass through that of the gate. Now during off, what will happen? There is a IG minus negative peak. So that will be applied to the gate automatically, faster rate to turn off the device. During on period, assumed that the equivalent constant current of IG on is being applied to gate of the MOSFET. So IG on is nothing but this is an average of this point. We will see that value also. So one can approximate the turn on surge current to right angle triangle. So now if you see this like a triangle, then the base that will give as a IG plus is a peak, then IG on is nothing but a peak by 2, that is IG plus by 2. There is an amount of gate current, so some charge will be supplied to the gate of the MOSFET. So that amount QG specified MOSFET is given, specific MOSFET is given in the manufacturing data sheet. So what is the QG? It will represent in the data sheet, and QG is nothing but you can see that time into current. So that is a, what is the time during turn on time, and what is the current, average current? This is a IG on. So this product will give as a QG. So from this what we can represent is one required to turn on the MOSFET faster, then the IG on is required should be more. So if you give more current, it will be turn on very fasterly. So the switched slower, then the smaller IGN would be enough. So only the thing is more charge carriers will reach to that reverse bias junction. It will be trigger faster. So for that reason, if you pass the IGN is high value, automatically device is going to be turn on. And if it is low, that is going to be take much time to turn on the device. Now you can see that is what the basic. Now there is a driver circuit MOSFET. In that MOSFET, now we can see that driver circuit, there is a resistor R1 as well as the resistor R2. There is a specific pulse is provided here. There is a pulse to that of the gate. And then there is a turn on in 1 microsecond. Then IGN is required would be 250 milliamperes of current we have to pass. To get devices on position with very less time, only 1 microseconds of time, we required as a 250 milliamperes of gate current, and IG plus, that is a turn on current, is 250 milliampere, and IG plus is obviously doubles of that. No, that is a 500 milliamperes of current. In the turn on time is 2 microsecond, then what will happen? IGN is required would be 125 milliamperes and the IG plus will be 250 milliamperes. Turn on gate drive surge current of IG plus only to limiting the resistor R1 can be connected in series with the gate terminal. So turn on gate drive surge current. To limit that current, we make use of a R1 surge current limitation. So then R1 is equal to what is the applied voltage? Here we are applying as a VCC divided by what is the peak current IG plus. That value must be placed here. So then what will happen? That is going to be minimize that current. So maximum allowable, you can see that IG maximum spike will be obtained. And the voltage is VCC. Then this much resistor you have to provide to limit the current. So there is a gate drive, this is VCC is nothing but a gate drive voltage, and generally it requires the 15 volts. So therefore VCC is a 15 volts is the most cases normally, and divided by IG plus. So then you will get it as a what is the R1, and this is the case. You can see that gate voltage is sufficient higher than the threshold voltage to turn on the MOSFET. That's why once if we pass the pulse way also, this voltage must be higher than the threshold voltage, and gate voltage sufficient lower than the threshold voltage, what will happen? It will be turn off. If you pass that voltage is higher than the threshold, or you can say that the device is going to be turn on. If it is lower than that, device is going to be turn off. There is a capability to sufficient charge in the input, that is a drive capability. It has to be capacitance, input capacitance, it has to be sufficient to turn on the device. And MOSFET gate resistance, this is a R1. We have observed that there is a protection. So then the resistor value should be selected because it is a affect the switching speed. If you allow more current in the faster time, it will be turn on first, means very less time, and otherwise it will be as a very time will be more. So in that, another one, there is a R2 resistor used. Resistor to reduce the gate source voltage to 0 voltage, then the input signal is open circuited. So we make to that, otherwise what will happen if this drop is more than the gate source voltage, required threshold voltage, then also IGBT is going to be turn on. But whenever we want to turn on the IGBT, at that instant only we need to give the gate signals. That's why it has to take care of that voltage potential will be 0 to maintain in the off state. And now the resistor R1 is used to limit the turn on surge current, and choose based on your R1 is this formula I mentioned, R1 is VCC by IG plus, and if the VG does not have a current sinking capability, the resistor R2 is connected in the parallel with that of device. In such, provide the discharge path to input capacitance and to maintain in the off state. R2 is usually chosen 10 times the value of R1. because R2 must be more. If the gate driven source VG can be sink current, and then R2 need not be used. So based on that protection, you can make use whether R2 has to be used, or preferably we can use that, but that value should not be to up to the threshold voltage. In such case, output resistance of the source VG is low, then the capacitance will be charged and discharged through the R1. So these are the what is the purpose of R1, R2, you can simply explain that. And other version also there is a possibility of use CMOS logic integrated circuit to faster switching of the device. There is another driver circuit will be, many driver circuits are there. We are explaining some of the driver circuit because practically once we are doing as a project or experimental in hardware is set up, if you use as a MOSFET or IGBT or any device, driver circuit is the major impact on that. We have to properly use the driver circuit to turn on the device and turn off, and snubber circuit. All these type of circuits are very essential in our application side once we are using as a any large application or project side. And this achieved by paralleling as a buffers, and either a CMOS hex inverting buffer and IC. There is a different ICs also available. Non-inverting hex buffer IC can be used to drive the MOSFET. And the input gate pulse signal source, that is a VG. This is the should have a polarity that should be appropriately respect to the type of buffer chosen, whether inverting or a non-inverting. So this is all inbuilt of device IC will get it. And the series resistance R1, which is used to limit the turn on gate surge current in the selected based on the R1 is VCC by IG plus. So the third one, we can see this arrangement is different, how the device driver circuit arrangement. This can be faster by using as a transistor to increase the turn on gate driven current. So that will be input capacitance of MOSFET provides the necessary forward bias to turn on the NPN transistor of a Q2. Any one is turned on, the consequently regenerative action will be takes place. So Q1 is turn off in the order to switch off the MOSFET. So this would be immediately a negative power supply is not needed, and this way we can able to turn on the device. So these are the simple if they asked as a driver circuits, these three simple circuit, and explanation small one or two lines you can give it. This is for either they asked as IGBT or a MOSFET. What we will replace here is a MOSFET is replaced with the IGBT symbol. Same gate will be as such. Here you make use of one thing, you can as a collector and then emitter. You can use this way, we'll make it as a IGBT. So that is the difference. So this is the end of our first unit. So now we'll start the next class, third unit. I think afternoon 3:30 to 4:30 is free hour. So I will take that hour also today. So now we just if on exam also there, I think exam on Thursday, and maybe at 5 o'clock or something. I will let you know the time in the LMS platform. So okay, now we can leave.